that I started to draw. So the key features are, as you noted, that the amplitude is stretched out to 3, so it goes 3 minus 3. Second, that it repeats twice as fast as an ordinary sine, so you notice this repeats after pi rather than 2 pi. And third, that it shifted 1 to the left, right? So this is compared to, wait, where did I draw that? It's over here. Yeah, compared to the ordinary sine, which would be 0 at 0. This one is shifted to the left, so it's 0 over here at minus 1. So those are the three things. Stretched, goes twice as fast, and moves to the left. Is that all happy?
Yes.
Okay, good. Just want to make sure that that's down pat since we didn't spend a lot of time on it. Okay, good. So then we were trying to do this last pretest question, which was find all theta such that this thing is true. And we simplified that to finding all theta such that sine 2 theta is a half. And then you told me that the half comes from the 30, 60, 90 triangle, and I pointed out that, good, so we need the two angles with the y value of the point on the unit circle being 1/2, and they both come from 30, 60, 90 triangles. So the next question is, what are those two angles that I've drawn here, the two pink triangles? What are the two angles which would give a sine of a half?
So that would be pi over 6 and 5 pi over 6?
Let's see. Yeah, that's right, good. Pi over 6 and 5 pi over 6. Okay, so here's the tricky thing. So this is the thing we didn't discuss before. So those are the two possibilities. So now we're actually going to get 4 possibilities when we take into account this 2 theta inside. And the reason for that is the following. So you correctly told me that the only angles which output this 1/2 are pi over 6 or 5 pi over 6. But the trick is that since this is twice theta, theta can wrap around the circle. Theta can wrap all the way around and come back to pi over 6. So if it's the case that twice theta, 2 times theta goes all the way around the circle and comes back to pi over 6, then that still satisfies this equation. Similarly, if theta goes all the way around the circle and then comes to 5 pi over 6, it will still satisfy this equation. So let me just write that somewhat more explicitly. We get 2 solutions that are kind of the obvious ones, right? You just take these 2 things on the right and divide by 2, because 2 times theta is pi over 6. It means theta can be pi over 12. So that gives us 1. Theta, I should probably draw a set since I'm using set symbols here. So theta can be pi over 12. It can be 5 pi over 12. But there's 2 more tricky ones, which are 13 pi over 12 and 17 pi over 12. So let me explain those a little bit further. Let's check what happens if we take one of these. So for instance, 13 pi over 12. What happens if we take twice that theta? So 2 times 13 pi over 12. Well, the 2's cancel, so that's 13, or what, 2 over 2, Jesus, over 12, sorry. So 2 cancels with the 12 to give us 13 pi over 6. But 12 pi over 6 is a complete turn around the circle. So this is the same as 2 pi plus pi over 6. So the point is that this value also satisfies the equation, because if I take sine of twice 13 pi over 12, I get the sine of 2 pi plus pi over 6. And the sine of 2 pi plus pi over 6 is the same as the sine of pi over 6, because I've just looped around the circle once and come back to pi over 6. It's a very long explanation and a subtle concept. So how do you feel about this?
I Yes, I understand this.
Okay, good. So you're happy with that, and you didn't even call me on that typo, 17 pi over 12. Good. Okay, so same thing. If I take 2 times 17 pi over 12, that's 17 pi over 6. That's the same as, let's see, 5 pi over 6, because I've just subtracted 12 pi over 6. Okay, good. So the punchline of this whole thing is that you have to be careful when solving trig functions, because even if there's only two angles on the unit circle which satisfy a particular equation, if you're multiplying the angle by something, you have to be careful about these wraparound solutions that go around the entire circle once. Okay. Other thoughts or questions about this?
I have no question.
Good. All right. So we've finished the pretest. If you understand all of these, then you have done all of the things that AOPS thinks you should be able to do before starting calculus, which is, I think, quite comforting.
And the thing is, their entire chapter 1 is review.
Yeah, I mean, quote unquote review. I imagine a lot of it was new for you, right?
Yeah, but like they're doing a pretest is supposed to let you know where you stand, not show that you can do the class.
Right. Yeah, I think it was useful for us to look at the pretest problems to figure out what we need to focus on, but it's not a bad thing that we couldn't do them at the beginning. So I think you can do all of them now, right? Or at least understand the solutions now, I think, right?
Yeah.
Good. Okay. If you have time, since I think if we go for 2 hours, then I can have 20 more minutes. I want to do a lightning couple of picture proofs about a couple other trig things that we haven't had time to really do properly, and then we can quit if you still have energy. Or do you have other stuff to do?
I do have to get a shower and work on some on-the-toilet stuff.
Okay. Do you want to...
But I can spare 20 minutes.
Okay. I appreciate your self-sacrifice. I'll try to do them quickly. Okay, so this will be pretty fast. So this is just to emphasize, right, the thing we saw last time is that even though we defined trig functions on the unit circle, we saw that other thing that by a similarity argument, any right triangle can be brought in contact with the unit circle, and then the trig functions apply to that triangle even if it's not on the unit circle. So the point of this problem is to show you that even non-right triangles can be studied using trigonometry, using a similar argument. So all I've done here is drawn a blue triangle. So this blue triangle is not right. See, it has 3 angles, which I've called alpha, beta, gamma, and this is a convention I like to use to help me remember angles and sides. So every angle is a Greek letter, and it's opposite the side with the corresponding English letter. So alpha is the first Greek letter, it's opposite the side A. Beta is the second Greek letter, it's opposite the side B. Gamma is the third Greek letter, it's opposite the side C. Is that all okay?
But I thought that the Greek alphabet was in a different order, so gamma was G. I guess I'm dumb.
Oh no, I think G is what is it, lambda or something? I don't know. Maybe it is in a different order and I'm just wrong, but
Oh Jesus.
I don't know. Well, even if I'm using the letters wrong, this is the variable I'm going to use.
Yes. Actually, it might be the exact same order, just that they don't start with the letter you expect them to.
Damn those Greeks. They're tricky. Okay, well, assuming the variables are reasonable enough, the question I'd like to ask is, what are the lengths of these 3 things marked in orange if I drop an altitude? So the pink line is dropped from the point which has angle beta, and it's dropped to be a right triangle. Or sorry, it's dropped to make a right angle with the opposite leg. So I've just dropped this down so we can use some trigonometry. So to start, if we just look at this triangle on the right side, so this right triangle here, what is the length of the pink line segment in terms of, say, A and gamma? Or even to start, I'll just ask an easier question. What is the sign of gamma in terms of maybe P for this pink thing? If this the pink thing has length P, what is the sign of gamma?
The sign of gamma would be the pink line over A.
Good. So if we want to solve for the length of the pink line, then that's P is A sine gamma, right? just multiplying through by a. So I'm just going to label that here. So I don't want to use the letter p. I want to express everything in terms of these a, b, c, and alpha, beta, gamma. So the pink line is alpha sine gamma. Is that okay?
Yes.
That came out sounding way bitchier than I expected it to. Okay.
Yep, totally.
Whiny, is that okay? Good. All right, same thing. What about this leg here? So this is this part that goes from the point that has angle gamma to the point where the pink line touches the base. What is the length of that bottom part in terms of a and gamma?
So that would be cosine gamma equals, oh god, whatever that side is over a.
Right, so cosine gamma equals this junk over a, which means this junk equals cosine of gamma times a, right? Just multiply by a. Is that all right, or should I write out that step?
I think that's good.
Good, okay. Good, all right, so that's this thing. That means that the other half, since the whole thing adds up to b, since I've just dropped this thing which cuts b in half, well, not in half, but it cuts b into two segments, that means the other leg on the left has to be, what, b minus a cos gamma, I think?
That sounds right.
Good. All right, so now this is where the punchline is going to come in. Now, since the thing on the left, this triangle over here, this left triangle is also a right triangle, so we can apply the Pythagorean theorem to it. And the three lengths of this thing are c is the hypotenuse, a sine gamma is one of the lengths, and this quantity b minus a cos gamma is the other length. So maybe I'll ask you, if I write the Pythagorean theorem, I'll start you off with the easy part. C squared equals, what should I write on the right side if I apply the Pythagorean theorem to the right triangle on the left?
I believe you should write a sine gamma squared.
Good, so a sine gamma whole thing squared, and what else?
And you add that to, I guess, b minus... Okay, this is quite hard to word. Should I just say b minus a cos gamma quantity squared?
Yep, that's perfect. That's exactly how you should say it. B minus a cos gamma quantity squared. When you say quantity, it signals to the reader, go back in your head to the beginning of that and square the whole thing. Good. Okay, so since you have shit to do, I will FOIL this out for you. So, well, the first one's not even FOIL. That's just a squared, that's a bad 2. A squared sine squared gamma, right? Just square the two pieces. When I square this, well, there's a b squared minus 2ab cosine gamma, right? Because you get two of those cross terms. And then plus a squared cos squared gamma. So this is going to be a test of your algebra chops to see how good your eyes are. What simplification, can you see the simplification that happens next? I claim there's two terms we can genocide. Can you see which they are?
It seems like there is some relation between the a squared sine squared gamma and the a squared cos squared gamma.
Good, yes, your eyes are getting much better. So if we factor out a squared, right?
Okay, that makes cool.
Now what happens to the thing inside parentheses?
Oh, this means that we can substitute it for, give me a sec. Oh yeah, we can just substitute for 1.
Yeah, exactly. So this whole thing is 1. So yeah, this, you should train your eyes when you, not only when you see cosine squared plus sine squared, but when you see some number like a squared times cosine squared and that same number times sine squared, you can always factor it out and replace the guts by a 1. So that's a nice trick. So now we're done. C squared equals a squared plus b squared minus 2ab cosine gamma. Have you seen this before?
I don't believe I have, unless we've done it in the past.
We have not. Your geometry class is an embarrassment. This is called the Law of Cosines. It's the most important formula for non-right triangles.
We literally did right triangles and ratios.
All right, well, this is a generalization of the Pythagorean theorem when the triangle is not right. So you can see what happens if I plug in gamma equals 90 degrees, or pi over 2. What's cosine of pi over 2?
Oh boy, that would be 0.
Right, so if the angle is 90 degrees, this term is 0 and it goes away, and we're back to Pythagoras. C squared equals a squared.
Oh, that's cool.
Right. But when gamma is not 90 degrees, or pi over 2, now we have a better version of Pythagoras that still tells us the relationship between the sides A, B, and C, but now you need to know this angle, which is no longer 90 degrees. This is very useful. I don't know what math class you're taking next year in cyber school, but you'll probably have to solve a lot of problems that involve using this.
So my plan is pre-calc.
Ah,
AP pre-calc.
how is there AP pre-calc? There's no AP.
I have no idea, don't question it.
That's mysterious. Okay. By the way, does that change any of the your goals for continuing with the calc group to meet, since you have now cyber school to meet your needs, or do you still want to keep doing this?
I want to keep doing this because technically cyber school is public and tax funded.
So the quality may not be that much better.
I'll keep my hopes up.
All right, we'll see. I'm enjoying doing this, so I'm happy to keep doing this if you have the time and interest. Okay, that's Law of Cosines. I don't care if you have this formula memorized. I care that you understand the proof, and if you needed to, under duress, if someone was holding you at knife point in an alley and asked you to derive it, that you could work it out. Because it's not that hard, right? All we did was start with the triangle, drop this altitude, and then label some things and apply Pythagoras to the left side. Right. So, good. One last thing. We're going to do another analysis that has a non-right triangle. So what I've tried to do here, not very well, I've tried to draw the same triangle 3 different times. So just as before, imagine that we have a triangle that has sides A, B, and C, and opposite side A is angle alpha, opposite side B is angle beta, and opposite side C is angle gamma. So that's the same in all 3 cases. But as we saw in the last problem, you can drop this altitude. It turns it into a right triangle. But you might have asked, what happens if I drop a different altitude, right? There's 3 choices. I can start with this one and drop the altitude this way, or I can start at the bottom right and drop the altitude like this. Is that clear that we have that choice?
Yeah.
Okay. So now let me ask you, what is the length of the altitude in each of these 3 cases? So I'll do the one of them for you. We want to use a different angle in each case. So in the green one, I'm going to use the angle gamma, and this is the same as what you told me on the previous one, I think, that this is just a sine gamma. Is that right? Is that the height?
I am thinking. That seems right.
Yeah, because sine gamma would be this chunk over A, which means this chunk is A sine gamma, right? So I think that's true. What should I do in the yellow triangle to get that height in terms of beta? So now we want to use the angle beta. How would I write this?
So we could use, once again, give me a second to think. I'm not going to explain it much, but this would be C sine beta.
Perfect. I'll buy it. If I think that you know in your head how you got to where you got, then I'm happy. Alright, so now we got one with gamma, one with beta, and I want one with alpha now. So what's the length of this one if we use alpha to get the length of the white line?
And in this case, it would be B sine of alpha.
Excellent, good. So you've gotten to the point where you can do these in your head pretty well. Unless you've seen
I want to avoid memorizing this.
Yeah, I mean, good. I mean, there's very few things you should memorize. Usually you should work it out. Okay, so now using the title as a hint, 3 formulas for area. We know the area of any triangle is a half base times height, but that doesn't tell us which height we have to use. So for instance, in the green triangle, if we look at this white thing as the height and say this is the height, then that means B is the base, right? So using the green triangle, the area is 1/2, base is B, height is A sine gamma. Cool.
Basin.
Basin gamma, yes, very good. I like when equations have a string of letters that spell something. It's very nice. Alright, so if we use the same thing in the yellow triangle, so now the height is C sine beta. What's the base if we use that height?
The base would be A. Yeah.
A, right. So the area is a half A times C times sine beta. That doesn't, axin is not a very nice thing to spell, I guess. But all right, so maybe you can do this in one step. What's the area of the pink triangle if we use this as the height?
This would be half of C. Wait, no. Yeah, half of C sine theta.
Or
Wait, that doesn't seem quite right. Half of C B sine theta. Yeah.
that's an alpha, but yeah, good. Half CB sine alpha.
Oh.
Good. Now we use the oldest trick in the book. We have 3 formulas for A, and we're going to use the very sophisticated mathematical results that A equals A equals A. So
Wow.
it's really quite, I mean, there's a good book on theoretical physics by Tony Z, and he says that the weapons of the warrior theoretical physicist are adding 0 and multiplying by 1. So here we do something, I guess it's multiplying by 1, that A equals 1 times 1 or something. But I'm just going to write those 3 things as being equal. So half BA sine gamma was the first one. So half BA sine gamma was the first. And I'm going to write this one for the yellow that you told me equals half AC sine beta. And then this third one is a half CB sine alpha. So a half CB sine alpha. Now this is not very symmetrical because there's, I mean, you know, they all have different letters and they all come with a half. So I'm going to do 2 things. First, I'm going to cancel all the halves because 1/2 appears in each equation, so I can just multiply by 2. Second, and I'm going to use a better color. Second, I'm going to divide all 3 equations by the product ABC. This is a very common symmetrization step. That if you have any 2 of a triple of variables, it's often nice to divide by all 3, because then 2 are going to cancel in each case, right? So in the first one, B and A cancel, and we're left with C downstairs. In the second, A and C cancel, and we're left with B downstairs. In the third, C and B cancel, and we're left with A downstairs. Is that all good, or was that too fast?
That's all good.
Okay. So when the dust settles, we have sine gamma over C equals sine beta over B equals sine alpha over A. Now this is very symmetrical and actually rather surprising, because remember, each of these letters comes in a pair where the angle is opposite the corresponding side, right? So we remember these were, for instance, if this is alpha, beta, gamma, and this is not a right triangle, this is any triangle, A, B, C. So we found that in any triangle, if you take the ratio of a side and the sine of the angle opposite that side, that will be equal regardless of which angle and side you pick. You can pick the first pair, the second pair, the third pair. They're all equal. So this is very useful for, I mean, if you know one of these but not the others, then you can get the other 2 ratios. Have you seen this equation before?
Nope.
What a fucking travesty. Alright, fine. This was supposed to be a big reveal. This is called the Law of Sines. Alright, fine. Good. Alright, so we've seen the Law of Sines and the Law of Cosines. Again, you don't have to memorize them, but the point is that trigonometry is useful for studying triangles even if they're not right. These things can be any angles, and we get this nice result, which goes with the Law of Cosines. Questions, thoughts, or complaints about this?
You're saving this as a YouTube video, right?
I am. Why? Do you want to review it later, or do you think other people will want to watch it?
There's some audio clips I want.
Like, what a fucking travesty.
Exactly.
Oh, I will be sad. Okay, there's one thing. Maybe we can do this. I'm just going to do this really fast because I want to be done with trigonometry. This is the last thing. We won't need it soon, but I'm just going to... This is supposed to look like a bullseye, but I just want to blaze through this very quickly. So you remember before...
Blaze it.
4:20, blaze it! It's 8 o'clock, so it's almost 4:20 or something. Okay, so you remember we used before cosine and sine to label points on the unit circle, right? Cosine theta, sine theta are the x and y coordinates.
Yes.
Good. So now I'm going to invite you to think about 3 circles with different radii. So one has radius 1, one has radius 2, and the third has radius 3. So my question to you is, if you had to give me somehow like an address system, like, I don't know, like a posting mail address, where you have to give me a list of numbers and it has to uniquely identify a point on any of these 3 circles, how would you design that? Like, what set of numbers could you give me that would identify any point on all 3 circles?
I feel like this is a reference to radians and / or angles.
I mean, not really.
I don't know.
I mean, the point is that if we were just talking about this one circle, what would your address system be? Well, then you would just give the angle theta, right? Do you agree that for any angle theta, I could uniquely pick out an address on the first circle? So you just go to that point, and then cosine theta, sine theta gives you that point, right?
Yeah.
So if I had 2 circles, there's an ambiguity, because if I hand you an angle, you don't know if I mean that angle on the first circle or that angle on the second circle, right? So I have to give you an additional data point. What new coordinate should I give to distinguish between these circles?
Perhaps the y value?
Yeah, I mean...
That's not very... That's not very informative.
Yeah, it would... I mean, it might help you if you know the y value... Like, if you're over here, the y value doesn't help you that much, because the y value cuts both circles. But you're saying that if I'm up here, the y value helps me because I know that up here it has to be on the second circle, right? I think that was your idea.
I guess so.
Okay. I think it might be easier to just give the radius and the angle, right? Because the radius is either 1 or 2, so it tells me which circle I'm on. And then theta gives me how far to go on that circle. So for instance, if the radius is 1 and the angle is pi over 6, then I know, aha, I go to the blue circle, I go over here to pi over 6, and that's the point that I pick out. But if I want that point on the bigger circle, I just tell you, it's kind of like a street address and a zip code, right? So you give me, the zip code is 2, so I go to the circle of radius 2, and then I go to angle pi over 6 on that circle, and it picks at that point. So do you agree if I give you both the radius and the angle, I can pick out any point on either circle?
Yes, but where's the mathematical basis?
Can you unpack that question? What do you mean?
It seems like you're making a procedure here.
I am. Yes. I'm just...
Okay, that's what you're doing. Okay.
The math question we're trying to answer is, how can I label points in the plane? And I'm starting by just thinking about 3 circles, right? Because if we just want to label any point on any of these 3 circles, I just give you a number 1, 2, or 3, and then an angle, right? So that labels any point on any of these 3 circles. So now I'd like you to imagine, instead of just 3 circles, we have infinitely many circles, right? So you could give me a circle of any radius, and then tell me an angle on that circle. So how many points, or what set of points can I now uniquely describe if I give you any radius and any angle? Can I get to any point on the plane with that numbering system? Like just pick a random point, this point over here. Can I get to that by telling you this is the radius and this is the angle?
I have no idea how to think about this. I'm just thinking something totally unrelated. I'm thinking back to how we did the hyperbola graphing x squared minus y squared equals 1 and all that stuff. Yeah, I'm totally not thinking of the right thing.
That's fine. I mean, in the hyperbola case, we were labeling points on that curve, right? So you're saying this is the curve x squared minus y squared equals 1. We want to label all the points on this. Now I'm just saying this is kind of the natural generalization of the things that we've been talking about this whole time, because trig was about labeling points on one circle. The hyperbolic trig functions were about labeling points on one hyperbola, or one arm of the hyperbola, right? Now what I'm trying to get you to see is we can generalize that procedure to label any point in the plane at all. If I give you a radius and an angle, that can get anywhere in the plane. So let me just draw it in a slightly different way. Instead of just 3 circles, let's pick any random point in the plane, and I could either pick that point out, describe it to you, by giving you its x and y coordinates, which tell you uniquely how to get there, right? You go x to the right, and then you go up by y. So that's one way of labeling the points. I give you those 2 numbers. A second and equally good way of labeling that point is to say, let's use that circle argument. So we pretend that this thing is on a circle. What's the radius of that circle, by the way, if that's x and y? Just by Pythagoras.
Oh boy.
Maybe I should.
The idea slipped my mind.
Well, let's see.
So, well, we already know that x squared plus y squared equals whatever r squared is.
Yeah.
But does that get us anywhere? I don't know.
Yeah, because if x squared plus y squared equals r squared, then you take the square root of both sides, and this is r, which is just square root of x squared plus y squared, right? See what I did?
Yeah.
Good. Okay, so any point x comma y sits on a circle of radius square root of x squared plus y squared. Now here's the tricky part. What's this angle? Or better yet, what's the tangent of that angle? Tangent theta. Opposite over adjacent, right? So have you forgotten your tangent?
I know that I'm just in deep thought about how to, I guess, word this.
Give me your unformed thoughts. It's more fun that way anyway.
So far, the only thoughts I have so far is that it has something to do with the inverse functions of sine and cosine. And it probably doesn't have any relevance to that at all.
Well, we will need an inverse function in a moment, but before even inverting, let's just write the tangent with no inverse, right? So tangent of theta is the opposite leg of the triangle over the adjacent, right? So,
Oh boy, I ignored the obvious.
oh, you were trying to write it in terms of something. Okay, well, in terms of y and x, what is tangent theta? How about that question?
SOHCAHTOA for the win. That would be y over x.
Good, y over x. So assuming theta is in the first quadrant, that means we can use this inverse tangent function. So theta is tangent inverse of y over x. If it's in a different quadrant, we have to worry about signs, but let's not worry about that for a moment. So this is what's called a change of coordinates, because a coordinate system is any way of labeling points in the plane in a way which is unambiguous. I give you a label and it picks out one point and only one point. One coordinate system is called Cartesian coordinates. I give you a point x comma y that unambiguously picks out this point because you go, for instance, a distance x to the right and a distance y up. A second and totally as good way of labeling that point in the plane is I give you a radius r, which is the radius of the circle that that point sits on, like the 1, 2, or 3 in the previous example. So that's the radius of the circle the point is sitting on. And I give you the angle with the x-axis that you need to move counterclockwise to get to the point on that circle. And to prove that those two ways of labeling points are just as good as one another, I've just written down two equations that convert between the two of them. It's literally just like a dictionary that translates from one to the other. So what we say in the lingo is that there's Cartesian coordinates and what we call polar coordinates. So the Cartesian coordinates are x comma y, the polar coordinates are r comma theta, and the dictionary between them, for the first quadrant at least, is r equals square root x squared plus y squared, and theta, again restricting to that quadrant, is arctan or tan inverse of y over x. Okay, so is it clear at least that either of these pairs of numbers will label a point unambiguously?
Yes, this is cool.
Good, okay. Questions about this, since that was... I know this is a bit more abstract, but what do you think?
I have no questions.
Okay, good. This isn't super important, but I think when we do parametrized curves later, this will come up, and I think it's useful, even if like there's no daily challenges about polar coordinates or anything, if you see it once, then when it comes up later and you have to learn it, your brain has been kind of chewing on it in the background for a while, so it will be easier. Okay, so I went over time a bit, but that's literally everything in the whole blitz. So yeah, this is all the content we'll need. So